So it is a pleasure to introduce Sourav Chatterjee, who will talk about KPZ behavior under arbitrary scaling limits. Sourav.
Okay, thank you for the invitation. It's a real pleasure. I have never been to Brazil, and so at least virtually, now I can give a talk. And so some of you may have heard about this talk, yesterday, which was in Canada in Montreal, the meeting. But I hope there are other people who haven't heard. And if I get some time, I'll tell something about the proofs also. So the KPZ equation models the growth of a generic randomly growing surface, and the equation, as many of you know, is the following. So if ftx is the height of a d-dimensional surface at a time t and a location x, the KPZ equation says del tf is nu times the Laplacian of f plus lambda over 2 times the gradient squared of f plus some other constant times a white noise, a space-time white noise. And here, space-time white noise formally is a distribution-valued centered Gaussian random field with this covariance structure is a product of delta functions. So it's basically, it's like having a Gaussian random variable with infinite variance at each point in space and time with the right infinity. And this can be rigorously defined as space-time white noise, but defining this is much more challenging. And a lot of work has been done on that. And very briefly, the KPZ equation was introduced by Kardar-Parisi-Zhang in 1986 as a universal model for random surface growth, in the same way that a Brownian motion is a universal model for many one-dimensional or even multi-dimensional random processes, but there, time is one-dimensional. So, sorry. Okay. So this is the study of the KPZ equation. And related topics is one of the most active areas in probability today, and there's a huge literature, and I will skip over this, in the interest of time. And of course, there are many resources where you can see the literature, all that's been going on and all that's been done. So let me only briefly mention something about KPZ, just to put it in a nutshell, that is, it's now well understood in one dimension, but remains a lot of questions remain in dimensions 2 and higher. Okay, so so one of the main problems in dimensions 2 and higher is that we do not know how to take scaling limits of approximate solutions to reach a non-trivial limit. Okay. So this non-trivial is a key word here. So it's in the non-trivial in the physics sense. And there are many, there's much to say about that. But even in one dimension, there can be many different scaling limits. But in many one-dimensional models, we know at least one way of taking a scaling limit that leads to a non-trivial solution. Okay. In higher dimensions, the question is less practical. In particular, 2 dimensions is the main case of interest because that's supposed to be the critical dimension for the model, and also surfaces are generally 2-dimensional. Although one-dimensional KPZ surfaces are also important. The interfaces, there are all these results that if you burn a sheet of paper, the boundary, when it stops burning, that's supposed to be like KPZ and that kind of thing. So physicists believe that for 2-dimensional models, there are these scalings which lead to function valued rather than distribution valued solutions. So in recent years, distribution valued solutions have been rigorously constructed in dimensions 2 and higher, but there is a belief that in the 2-dimensional case, there is a way to construct function valued solutions of the KPZ equation. So this is a rather strange situation that, that for Brownian motion, for instance, there are no, 2 different Brownian motions. So there is only one Brownian motion that you can construct. But for KPZ, it's not clear what's the right definition yet. So in dimensions 2 and higher. Even in dimension 1, that was a question for a long time. So this I don't really understand very well. So there is numerical simulations, but about these conjectures, but they remain out of the reach of rigorous math. So so in one dimension, sorry. So in just a minute. Sorry, just 1 minute. I'll have to somebody else.
Esta gente está no video.
Okay, sorry about that. Yeah, so I'm at home. Okay, so this in this talk, I'll take a small step towards understanding this KPZ without confronting this issue of scaling limits. So this is just I was trying to understand this, what's going on with this KPZ growth, and this, I'll tell you what and some results I have. So this approach was based, is based on a framework introduced in some recent papers that I wrote last year, and joint work with Suganidis. And so one of the things is that since the correct way to scale is mysterious, the following workaround is proposed here. So consider a general class of growth models which contains at least one model of interest, okay? And then show that irrespective of how you take a scaling limit, since we don't know what's the right way of taking a scaling limit, there is not even a very precise proposal. We show that irrespective of how you take a scaling limit, the growth is always, there is a local KPZ behavior, meaning that the growth, instantaneous growth, breaks up as a sum of a Laplacian term, a gradient squared term, and a noise term, and a residual term that's negligible compared to the other three terms and their sum. Okay. So surprisingly, this turns out to be doable. So I'll tell you about that. Okay. So first, let me define local KPZ growth. It's a pretty general definition, so we'll see here that suppose you take some dimension bigger than or equal to 1, and suppose you have that we have a collection of random functions f epsilon, epsilon positive from z, non-negative integers cross z to the d into r. So these are random surfaces. Okay, so these are random surfaces which are defined in a discrete setting. So you have time discretized as non-negative integers, space discretized as the lattice z to the d, and f epsilon tx is the height of the surface at location x on the lattice and at time t. Okay, so that's the evolution of the surface, and then you have some scaling limits. So alpha, beta, and gamma are positive real numbers depending on epsilon, so that alpha and beta tend to 0 as epsilon goes to 0. Okay. And then you define the rescaling of the surface as follows. So f super epsilon tx. So now this t and x are real valued. So t is a non-negative real number, and x is an element of Euclidean space, d-dimensional Euclidean space. You define f epsilon tx as some multiplicative factor gamma, so this is a multiplicative factor, times f epsilon at these rescaled values. So you scale time by alpha and you scale space by beta. And these are the ceilings, so you take the integer parts above, okay, coordinate-wise. So these are all coordinate-wise. And this means that we are rescaling space and time so that successive time points are separated by alpha and neighboring points in space are separated by beta. Okay, so this is how you rescale your lattice, you rescale your space and time. And this is just a multiplicative factor. So I have no constraint on the multiplicative factor. It can blow up to infinity, go to 0, or remain constant. But alpha and beta have to go to 0 because the lattice is getting finer and finer. So So these are the constraints that I have, that alpha and beta have to tend to 0 as epsilon goes to 0. Okay. Okay. So sorry. Okay. So yeah. So this is what I said, that this is just a multiplicative factor meant to ensure that the limit of f epsilon as epsilon goes to 0 on some appropriate space of functional distribution is non-trivial. So this is just meant to ensure that. Okay, so that's the first step. So is this clear? You just have some generic, some general, surface growth model on the lattice, and then you're taking a scaling limit of that. Okay, with no constraints until now. Okay, and so now let A be the set of consisting of the origin and its nearest neighbors in the lattice, and then you define your local average of this function f as follows. So you have this function f on this rescale lattice. And then you just take f at a point and its neighbors in space and nearest neighbors, and you take the average of those values. Okay, so they just this local average. And then you define this approximate time derivative of f as exactly what you would think. You take one step in time, you take the difference in f, divide by the length of that step. So alpha, remember, is the difference in the spatial, in the time coordinate. Okay. And you take this approximate time derivative, then you define the approximate Laplacian as this local average minus the value at the point, divided by beta squared, just exactly as you would imagine a Laplacian to be. So you define an approximate Laplacian, approximate squared gradient as this, which is, you take all the neighboring values, you subtract of the average value. So there is a thing about that. Why aren't you subtracting of the value at the point? But so it leads to some subtle differences. And you have this and divide by beta and squared. So you define these approximate time derivative, approximate Laplacian, approximate squared gradient, so discretized versions of these things on this rescale lattice. Okay. And these definitions are inspired by the fact that if alpha and beta go to 0, if the lattice scaling, the spacings between neighboring time and space points are going to 0, and f epsilon, your sequence converges in some strong sense to a smooth function, then this approximate time derivative Laplacian and squared gradient converge to the right quantities, right functions. Okay, so that's some reason, and that's the motivation for these definitions. Okay, but of course, in general, we don't expect this to converge to a smooth limit, but we can still keep these definitions as this as local, local perturbative behavior. So here's the definition of local KPZ growth. So you have this sequence of random functions on this rescale lattice. And we say that this has local KPZ behavior if for some new lambda and d, depending on epsilon, and some random map psi and r, we have that for all t and x in this Euclidean space, these approximate time derivative is this nu times the approximate Laplacian plus lambda over 2 times the approximate gradient squared plus square root d times this field psi plus some error. So there's an exact equality such that the following hold. The noise field converges in law to white noise. So there are different notions of convergence of distribution, random distribution. So I have, in the paper, you can see the precise notion that I'm using. So the noise field converges in law to white noise on this space as epsilon goes to 0. And the remainder term is negligible compared to the first 3 terms. So the remainder term divided by the first term, the whole first term with the coefficient, goes to 0 in probability as epsilon goes to 0, and similarly for the second term and third term, and also the sum of the first 3, just to emphasize that there is no cancellation. Okay, so you really have that this field. Okay, this field, the instantaneous growth in this field at individual locations, does show this KPZ type of behavior, that it breaks up as some coefficient times the Laplacian plus some other coefficient times the gradient squared plus some other coefficient times white noise. And the only global thing here is that the white noise is converging, this approximate white noise is converging to a real white noise as epsilon goes to 0. But everything else is local. So I'm not integrating over anything. So I'm just having everything else is is having a local behavior. Okay. So any questions about this definition? So sorry, it's a little bit notationally heavy with the rescalings and all that, but you can just imagine it as follows. So you have this lattice, okay, the space and time, and it's rescaled. So the lattice, spacings are very small. In the spatial direction, maybe they have a different scale than in the time direction, but overall the spacings are very small. And then you have this random function. For each epsilon, you have this random function, and you define the approximate time derivative, approximate Laplacian, approximate gradient squared in the usual way you can imagine that you define it in the discrete sense. And then I'll say that it has local KPZ behavior if this happens, that this approximate time derivative is expressible as this sum of these three things, sort of like the KPZ equation, plus an error term, which is very small. Okay. Okay. So here are some remarks. First of all, it may seem as if this new lambda and d should not be allowed to vary with epsilon, since the coefficients of this Laplacian gradient squared and white noise in the KPZ equation are formally written as constants. But this is not quite true. In the KPZ literature, it's understood that the coefficients can be allowed to vary when taking a scaling limit, or even be allowed to tend to zero or blow up to infinity. Okay, so the main thing here is in the definition is that the error term is negligible compared to the other three terms, even after you put down the coefficients. So, but the three terms themselves may not be comparable. One may be much larger than the other. Okay. And this is especially true in dimensions higher than one. For example, in 2D surfaces, this is supposed to be true, that these coefficients should vary with epsilon, and we'll see some justification for that why you must have coefficients varying with epsilon as you are taking away the smoothing. Okay. So one more motivation for this, which is that this motivation for local definition comes from this eventual goal of creating a universal framework for scaling limits of discrete surface growth analogous to diffusion approximations of Markov chains. So recall that the diffusion process adapted to filtration F is characterized by these local growth conditions, that the expected first moment of the difference conditional on everything up to time t is some axt times h plus little o of h. And expected value of xt plus h minus xt squared given ft is like bxt times h plus again little o of h. And the expected cube is little o of h. So this behavior sort of characterizes the diffusion process. And so this gives an informal description of the stochastic differential equation dxt is axt dt plus square root bxt dbt without actually defining it rigorously. So this is sort of a prelude to this, that you want to define this equation, but you have this behavior. And this is one way the diffusion approximations are proved, that you start by proving these kind of behavior for the process, and then from that you arrive at limiting process. Okay, so the purpose of local KPZ growth is to do something similar for surface growth, and this is entirely motivated by this kind of background that can we have some kind of local growth criteria which one can then hope to make rigorous, give a global framework from that. Okay. So now let me tell you the main result of the talk. So it needs a couple of slides of preparation. So recall that A is the set of the origin and its nearest neighbors, and let phi be a function from R to the A into R. Okay. Let Z be a collection of IID random variables, which we'll refer to as a noise field. Okay. So for each point in time and space, you have a random variable, and we assume that these random variables are IID. And here's the main growth process. So now everything is not rescaled. It's just have things on a lattice. But there is a parameter epsilon here. So consider a function f epsilon as follows. You start with all 0 for simplicity. You start with all 0. And then you define the height at, so ftx denotes the height of the surface at time t and location x. So at time t plus 1, the height would be a function, this function, applied to these values, which are the heights at location x at time t, but also at locations that are neighboring to x at time t. So you look at all the heights at location x and its neighbors at time t, you apply this function to that collection, plus you add epsilon times the noise. So the epsilon only comes in here, okay, in these recursions. Phi is not dependent on epsilon. So you add a small amount of noise, after you make the height grow according to a certain function. Okay, so imagine this. So this is what I said, that this is the height of a d-dimensional surface at time t and location x. And this recursion says that the height at time t plus 1 is a function of the heights at x and its neighbors at time t plus an independent random fluctuation. Okay. And this is the framework that I have been investigating for the last 1 year, which is this kind of growth, general growth without looking at a specific model. You have a general framework where you have this kind of recursion that is the height at time t plus 1. So this clearly is a Markov chain on the space of surfaces. So if you consider all surfaces on the infinite lattice z to the d, this defines a Markov chain. Okay. So this is a general kind of Markov chain where the surface at time t plus 1, the heights at each location are functions, arbitrary functions. Will impose some conditions on the function, some arbitrary function of the heights at that location and its neighbors, and then you add random noise. And also you can have more general things, which I'm not presenting here. You can have the noise inside the function also. So you can have that overall it's a function of the heights and the noise, and you apply some nonlinear map to that, and you get a new height. Okay, so I'm here in this talk, I'm just talking about additive noise. Okay. So we'll see later that the model of directed polymers in a random environment can be put in this framework. So that's one model that's widely studied. That can be put in this framework. So any questions about this setup? Okay. So here let me make some assumptions about phi. So first, some notation: let 1 denote the vector of all ones. For u and for a vector u, let u bar denote the average of its coordinates. And for u and v, we write u bigger than or equal to v if u dominates v in each coordinate. So we make the following assumptions, and these assumptions, as I found later, that they are quite commonplace in the PD literature on viscosity theory and so on. So we first assume that these are equivariant and constant shifts. So what this just means is that if suppose you have a surface and you have another surface which is just a constant shift of that, so you just increase all the heights by a constant, then if you apply this procedure, with the same noise for both, the resulting surfaces that you would get would also differ by the same height. So it just has this effect of shifting everything up by a constant. That's the equivariance and the constant shifts, and that's a very reasonable thing. 0 at the origin, this is not really an assumption. I mean, it can be incorporated by subtracting off just a constant. It doesn't affect anything. Monotonicity, which just means that if one surface is completely above another at time t, and you apply the same noise, then at time t plus 1, also the first surface will completely dominate the other. And that's also reasonable. Symmetry, so this is a simplifying assumption. This can be relaxed, but it leads to some nice structure. I assume that the function remains unchanged under any permutation of the coordinates. Regularity, this is a strong assumption that this function is twice continuously differentiable. And actually, this seems to be important for KPZ because, in my work with Suganidis, we have considered functions which are not C2, other kinds of functions, and they lead to other kinds of equations. Okay, so that's so there are these other things that are going on. And non-degeneracy, this is the Hessian matrix of the function at the origin is non-zero, just at the origin, nowhere else. I'm assuming that at the origin it's non-zero. It's a local condition, but being C2, it forces it to be non-zero in a neighborhood of the origin also. And this assumption is necessary to ensure that you do see the gradient squared term in the KPZ equation. So it's not just a stochastic heat equation. And these are all some regularity assumption, but there's one more assumption, which is the crucial one, which leads to this, KPZ, local KPZ behavior under arbitrary scalings. It's this assumption of Edwards-Wilkinson domination. So the Edwards-Wilkinson surface growth model fits into this framework with phi u equals u bar. So it's a very simple model. It was proposed before KPZ was proposed in 1982, I think. And the model is just that you have the heights at time t. What you do at time t plus 1 is just you take the average of the heights at x and its neighbors, and you add a constant. So it's just, the function is now just the averaging function. So you just take the average height, plus you add a noise. And so for those of you who are familiar with stochastic heat equation, it's immediate that this should be, the scaling limit should be the stochastic heat equation, and it is. And then you can completely analyze this model. It's a nice simple model, but doesn't give rise to KPZ behavior. I mean, it almost does without the gradient squared term. And we assume that our surface grows at least as fast as Edwards-Wilkinson. So that is, the function that you're applying is at least as large as the average value. Okay, so it's not less than the average value. So the function cannot be the minimum of the heights at time t at locations neighboring to x, for example. Okay, so that's one example which is not allowed. And moreover, we assume this domination is strict in this sense, but this is a technical condition. So so if un is a sequence that phi un minus un bar is going to 0, then un minus un bar times 1 is going to 0. So you cannot have that, this is not holding. So if u is non-zero, then this is a strict inequality. That's essentially what it's saying, but also at infinity. Okay. So this seems to be, I don't know why this is an important condition, but this seems to be what's needed for the whole thing to go through. So what we'll see is that, what you really need is the following. Okay, so let me tell you intuitively what's going on. So you have this surface which is starting with all 0. And at time 1, you are just applying this function phi to that surface, and you're adding a small noise at each point. So at time 1 also, they're all, the neighboring heights are all pretty close to each other. The surfaces, if you take 2 neighboring points, the height difference is order epsilon. And you keep going like that for a while. Okay, so then you expect that after a while it starts breaking down because this epsilon is remaining fixed, but time is going to infinity. So you'd expect to see larger and larger differences between neighboring heights. Okay, and this is, for example, this happens if you have some process like the one that's considered recently in this paper of Canizaro and Harrer on this Brownian castle. They consider infinite temperature ballistic deposition. So they introduce a temperature term in ballistic deposition, and they introduce infinite temperature, where you are basically you have a ballistic deposition process where a brick is falling from infinity, but instead of it attaching to the highest column in a neighborhood, what it does, it chooses a column at random and attaches itself to that. So that kind of thing. So that kind of process, it's not dominating the Edwards-Wilkinson surface growth. And in that, you will see that neighboring heights the differences between neighboring heights can become very, very large as time goes on. But this condition somehow ensures that the differences between neighboring heights remain close for all time. If epsilon is small, they remain order epsilon, or maybe root epsilon forever. So no matter how far you go in time, it can be some function of epsilon, or it can just be infinity. You can go to infinity, but the differences between neighboring heights remain of order epsilon. They don't change. Okay, and that is the key thing. So that is why you will see this KPZ behavior under any scaling limit that you want. The scaling limit will not interfere with the local KPZ behavior, and this is the key to that. Okay, so this is the assumption of strict Edwards-Wilkinson domination. And we'll later see that in a model of directed polymers in random environment satisfies all of these assumptions. So there is this one model which satisfies all of these assumptions, but you can construct other models also. And some small technical assumptions about the noise field. We assume it's mean 0. We assume it's bounded. So I don't know if this can be dropped. Probably this can be dropped. We assume that they're absolutely continuous. The law of ZTX is absolutely continuous with respect to Lebesgue measure. And then we define our rescaled surface. So let f epsilon be defined using this phi, the noise field, as we defined earlier. And then you take any alpha, beta, and gamma, where alpha and beta go to 0 as epsilon goes to 0, and define the rescaled surface like this. Okay, so you have your original f epsilon on the lattice, but now you scale space by beta and scale time by alpha, and then you multiply the result by gamma, and you get a rescaled function. And so here is the main theorem. So suppose all the stated assumptions about phi and z are satisfied. Let f super epsilon with the rescaled surface defined in the previous slide. So you start with f sub epsilon, which is just a sequence of heights on the lattice, and then you rescale that by this alpha, beta, and gamma. And the sole condition you have that is alpha and beta have to tend to 0 as epsilon goes to 0. So then as epsilon tends to 0, these rescaled surfaces have local KPZ behavior with these coefficients. Nu, lambda, and d will depend on epsilon. So nu will be something like beta squared over alpha, lambda will be like beta squared over alpha gamma, and d will be like epsilon squared beta to the d gamma squared over alpha. And there are some numbers which are coming from the model. So sigma squared is the variance of the noise variables, q is the value of the diagonal elements of the Hessian at 0, which are all equal by the symmetry, and r is the value of the off-diagonal elements. And these are unequal because this is a non-zero matrix. So you have this kind of behavior. So you have this general setup of the surface growth where the function the height at a location grows as a function of the neighboring heights plus some random error. And then I'm saying that if the random error is of order epsilon, and you have the surface and rescale it by some alpha, beta, and gamma, you take any scaling of space and time as epsilon goes to 0, you always see the local KPZ behavior. Okay. So the infinitesimal growth at the height breaks up as a sum of Laplacian plus gradient squared plus random noise plus negligible error term. Okay. So any questions about the theorem? Okay. So here's a remark. So suppose we want this new lambda and d to remain bounded above and below by constants as epsilon goes to 0. So just like in the KPZ equation, suppose we wanted them to stay constant, and so that this business about them varying with epsilon doesn't arise. So recall from the previous slide. So I'll just write it down. So nu is like beta squared over alpha, so up to constants. Nu is like beta squared over alpha. Lambda is like beta squared over alpha gamma. And d is like epsilon squared beta to the d gamma squared over alpha. Okay. So if you want nu to be order 1, we need beta squared to be like alpha. And plugging this in the next equation, we get that lambda is like 1 over gamma. So if you also want to let lambda is of order 1, we need gamma to be of order 1. And finally, so if beta squared is like alpha and gamma is order 1, if we further want d to also be of order 1, then using these two facts, plugging them here, so beta squared cancels with alpha and gamma is order 1. So you get epsilon squared beta to the d minus 2 is of order 1. Okay. So, but since as epsilon goes to 0, we need alpha and beta to tend to 0. That's the only restriction we have, that if as epsilon goes to 0, alpha and beta have to go to 0 also. So then this would be impossible unless d is 1. Okay, if d is 2 or more, you cannot have this, and simultaneously have beta going to 0 scaling. So there is no way to have the coefficients behaving like order 1. There is no rescaling scheme that we can take which will ensure that these coefficients remain of order 1 if d is 2 or higher. Okay, so you necessarily have to take some of the coefficients to 0 or infinity as epsilon goes to 0. When d equals 1, this tells you that beta should be like epsilon squared, and then we also have beta squared is alpha, so alpha should be like epsilon to the 4th, and gamma, as we reduced, should be of order 1. So this is the only way you can have that these coefficients, this new lambda and d are constants, is to take gamma of order 1 and beta like epsilon squared and alpha like epsilon to the 4th. And we'll see later in a couple of slides that this is the intermediate disorder regime. When we're applying to polymers, this gives you the intermediate disorder regime of Albert, Scamming, and Quastel. So this is one of the models, one-dimensional models in which convergence to KPZ was proved. Okay. Okay. Any questions about this? Okay, so recall that A is this set. So let's consider a specific function now. So I'm just talking about general functions. So this is one specific function, phi, which is log of 1 over 2d plus 1 summation over a e to the ua. Okay, so they consider this specific function on R to the A. And it's easy to check that this is equivalent on a constant shifts. It's 0 at the origin. It's monotone, symmetric, C2, and the Hessian at the origin is non-zero. And moreover, the Hessian is positive semi-definite everywhere, which shows that this is convex, this function. And the following lemma now shows that this satisfies this Edwards-Wilkinson domination. So if phi satisfies all of the other conditions and is moreover convex, then one can show that phi satisfies the strict Edwards-Wilkinson domination. Okay, so this is one condition, but you can easily construct other phi which are not convex but still are satisfying the Edwards-Wilkinson domination condition. So convexity was one thing that guarantees this domination in the presence of the other conditions, but it's not necessary. There are other easy to construct other phis which satisfy this. Okay. So why this particular phi? Okay, it seems like a pretty arbitrary choice. The reason is that with this phi, you can actually solve the recursion and write down the function explicitly. And this is what it comes out to be. So let f epsilon is a discrete random surface generated using phi displayed in the previous slide and this random field. And then by induction on T, you can show this, that f epsilon Tx is log of a partition function. So log of the sum over all lazy random walk paths of e to the epsilon times the sum of the noise variables along the path. Okay. And this is the log partition function. So you don't have to look at this carefully now. But let me just say that there's a log partition function of the d+1 dimensional directed polymer model on lazy random walk paths of length t-1 to inverse temperature epsilon in the random environment Z. Okay, so this is basically a random surface generated by this directed polymer model. Okay, and so since we have this whole thing in this framework, we now arrive at the result in the next slide. So consider the random surface generated by the d+1 dimensional directed polymer model at inverse temperature epsilon. So now epsilon becomes inverse temperature. Then the surface behaves locally like this. The discrete time derivative is equal to some constant times the discrete Laplacian plus some other constant times the discrete gradient squared plus square root d times something that approximates white noise. So sorry, I forgot to write that, but this is converging to white noise plus a lower order error term as we send epsilon to 0 and scale space and time in any way we like. Okay, and these are the discrete approximations. Okay, and I wrote that, yeah. Psi is an approximation of white noise, and these are functions of epsilon and a choice of space-time scaling. So I displayed the exact formulas in the previous slides. So this is the theorem that for the surface generated by directed polymers, you have this local KPZ behavior under any scaling of space and time. And sorry. Okay. So this is the application. So it's just putting this particular function phi in this framework, we get this result. And so just a remark, connecting it to the previous remark, that Alberts, Cannon, and Quastel showed that a non-trivial KPZ limit can be obtained for the 1+1 dimensional model by taking, so if you consider polymers of length n, you have to take the inverse temperature proportional to n to the -1/4 and look at polymers in a special window of n to the half. And this is called the intermediate disorder regime. And in our language, length of the polymer is 1/alpha, because alpha is the scaling of time, and the special window has weight 1/beta, because beta is a spatial scaling, and the inverse temperature is epsilon. And so the intermediate disorder regime is equivalent taking alpha to be like epsilon to the 4th, and beta like epsilon squared, and gamma to be a constant. Gamma is just a multiplicative factor. So in this paper, they just take the surface, they don't multiply it by anything. And as we saw earlier, this is the only way that to have the coefficients in the equation do not depend on epsilon, to have them constant. So the intermediate disorder regime is the only way to do that these coefficients in this local KPZ behavior, the coefficients to be constant. And as we saw in dimensions 2 and higher, there is no way of doing it. Even for directed polymer model, there is no way to scale space and time as you send the temperature to 0 to have to have that local KPZ behavior with constant coefficients, but you can have local KPZ behavior with coefficients that vary with epsilon in many different ways. Okay, so any questions? Okay, so all right, so these are the results I have, and I don't quite know if I have enough time to tell you the proof, but maybe I can try a little to tell you about the proof. How this result is proved. And as I told you, the main thing here is that the main thing that the proof or the theorem is saying is basically that these surfaces, as they grow under these conditions on the growth function, the phi function, it has this nice property that neighboring heights remain closed. So you can apply analysis to try to understand what's going on. And so perhaps even further analysis going beyond the local to global can also be done, but that's for the future. So let me tell you a little bit about the proof. So you have these functions f epsilon. You have the local averages, which is just the average value of the function in a neighborhood. And suppose you know that at time t and x, which can depend on epsilon, t can be very large. Suppose you know that at some time you have that the neighboring heights are close. Okay, where close means close. The difference is going to 0 as epsilon goes to 0. Okay, so then using Taylor expansion and the properties of phi. Okay, so the properties come in quite crucially. The first set of properties that I showed, that you can show that you do already see this KPZ kind of behavior. You can show that the time derivative is like the Laplacian plus a gradient squared plus some noise plus a remainder term of smaller order. So this, I'm not showing this, but it's a calculation, and it uses these, monotonicity and the equivariance and all those properties and symmetry and all those properties. And using those properties, assuming that the neighboring heights are close, you can show that KPZ kind of behavior comes up. Okay, quite generally. And this K depends on this phi. And for some phi, this may be 0, where you just see a stochastic heat equation kind of growth, but more generally, you do see the gradient squared term. Now, so to get the local KPZ behavior under arbitrary scaling limits, you need to have that this thing, that these neighboring heights are close, even if t and x are allowed to vary arbitrarily as epsilon goes to 0. Okay, no restriction. So you can have this t and epsilon varying arbitrarily as epsilon tends to 0, and that's the main thing that you have to prove. Okay. And so now there are no estimates that you can do here, because this phi is sort of completely arbitrary and it doesn't have any contraction properties or anything that you can exploit for this. So how do you do this? So recall that ft plus 1 at x is this function phi applied to ft x plus a over all neighbors of x plus this random noise. Let del a phi denote the derivative of phi in a coordinate a. Okay. And by equivariance of constant shifts, you have this, and taking the derivative with respect to c at c equals 0 shows that the derivatives of phi over the coordinates should add up to 1 at all locations. So the phi is a function which has a property that if you take sum of its derivatives, partial derivatives, they always add up to 1. And by monotonicity, the partial derivatives are non-negative. Okay, so combining these two, you see that at any point, the derivatives of phi are non-negative and sum to 1 and define a probability measure. Okay. So you can use this to define a random walk. So fix a realization of the growing surface, and then define a random walk on the lattice as follows. So you take any t and x, you start the random walk at location x and at time t, and then it goes backwards in time until time reaching 0. And the rule is as follows. If it is at a location y at time s, then at time s minus 1, it moves to a neighbor of y with probability exactly equal to the partial derivative of phi applied to this whole bunch of values, which are the heights at time s minus 1 at the neighbors of y. And you know that this vector this probability, this derivative, if you sum up over all the neighbors, you get 1, and these are non-negative. So this defines a legitimate random walk. So given a realization of f epsilon, you get a random walk from each location and time point. You get a random walk going backwards in time. So this shows, well, from this one can show the following. This is my main goal that I use this random walk to do, which is that if you take the height of the function at time t and location x, it's a very complicated function of all the noise variables because it's iteratively applying this phi again and again. But you can write down its derivative with respect to a particular noise variable explicitly as epsilon times the probability that the random walk passes through that y at time s. Okay. And this epsilon comes because we have additive noise. If we don't have additive noise, if the noise is inside the function, then you will have some other factor here, but this probability is still going to appear. Okay, and this is, note that this is conditional probability given the realization of f epsilon. Okay. So you can write down the derivative of the height with respect to a noise variable. You can write it down as, it's not a simple thing. It's the probability of a complicated random walk, but it is still something you can write down. Okay, but this is quite useful. So why is this useful? It's because if you look at this, you will see that what happens if you fix this time s and you sum over all y. If you sum over all y, this sums to 1. Okay, so this is non-negative because the right side is non-negative, and the sum to epsilon. Okay, so this is what we get. That for any s, so I just put the absolute values for emphasis, but this is without absolute values. Also, this is true because it's a non-negative. If you sum over all y and you take all the noise variables at time s and you take derivatives of f epsilon, some height at time t, with respect to these noise variables, the sum is epsilon. Okay, the sum is quite small. So what this means is that, for example, if you replace all the noise variables at time 1 by 0, so you just take away all the noise variables at time 1, just replace them all by 0, then the value of any height after that, the value changes by at most b times epsilon, where b is a constant upper bound on the magnitude of the noise variable. So this is where I use the noise variables are bounded. So I just take all the noise variables, replace them by 0, then the height at any point after that changes by at most b times epsilon. So there is not much change if you change all the noise variables at time 0. Okay. So let g epsilon tx be the value of f epsilon tx after replacing all the noise variables at time 1 by 0. But now note that if you replace all the noise variables at time 1 by 0, what happens is that the new height function that you get is actually 0 at time 1. Instead of, it's 0 at time 0, but it's also 0 at time 1. Okay, it's not changing. So this new height function is just like the old one in law, except that it's starting with all 0 initial condition at time 0, we start with an all 0 initial condition at time 1. Okay. So therefore, in particular, it implies that the g epsilon t plus 1x has the same law as f epsilon tx. Okay. So this shows the following, that the expected difference in height between time t plus 1 and time t at a particular location, you can replace the second term by g epsilon t plus 1x, but then you know that this difference is bounded by b epsilon. This is what we showed, that these two height functions differ by b epsilon. So this difference is, so this expected height difference is bounded by b epsilon for any x and any time. Okay, so this is the first step, that the function is not growing very fast. Even if you go very, very far away, it's always controlled. The amount of the amount of growth it has in one time interval is very small. So now the next thing is that this all 0 initial condition means that the law of f epsilon is the same, tx is the same for all x. So you can replace in this expression, you can replace f epsilon by its local average. You take its average over all neighbors, and the expectation remains the same. So it's again bounded by b epsilon. Now recall that f epsilon t plus 1x is some function, this phi applied to all the heights at the neighbors of x, plus some random noise, and noise variables have mean 0. So the expectation is exactly expectation of phi with all these heights at time t and locations at the neighbors of x. Okay. So then what you do is the following. You consider a vector q epsilon tx, which is the heights at at locations neighboring to x at time t minus their average value. So it's a vector. Each coordinate represents a location neighboring to x. Okay, and you take the height differences between the difference between the heights at location minus their average value, and that's your vector. And if you apply phi to this vector, by equivariance, this f bar will come out of phi, and you will get exactly this expression here. Okay, so expectation of phi of q epsilon tx is bounded by b epsilon, where phi, q epsilon is this vector, and this inner expression is just this thing here, what I wrote down here. Okay, well, plus this error which has mean 0. So anyway, so this is what you get from all this, and even if you kind of lost track here, but don't worry. So what we end up here is the following. So you have that f epsilon t x plus a over all neighbors of x, okay, minus the average value. You have this whole vector, and if you apply phi to this whole vector, you get some number which has expected value less than b epsilon. Okay. So now note that this vector belongs to this hyperplane where the average of the coordinates is 0, because this is just taking these heights and taking off their average values. The average of the coordinates is 0. By Edwards-Wilkinson domination, phi is non-negative everywhere in this hyperplane. Okay, so that's the Edwards-Wilkinson domination, says that phi applied to a vector is bounded below by the average of the coordinates of the vectors. So this phi is non-negative everywhere in this hyperplane. So you can apply Markov's inequality to get this bound, that the probability it's bigger than eta is bounded by b epsilon over eta, because we know that its expected value is bounded by b epsilon. So it's non-negative, which means that phi of q epsilon tx has a small value with high probability. Now, by the strict domination, we know that if you have a sequence un going to 0 on this hyperplane, then phi un should also go to 0, which implies that if you take given any delta, you can find an eta so that if phi u is less than eta, then u is less than delta. So phi being small means that the vector itself is close to 0. So this shows that the vector itself, the vector of all the neighboring heights minus their average value, has a small norm with high probability. Okay, by a correct choice of delta, you can prove this. So note that this bound has no dependence on t and x. So this is completely independent of t and x. It just depends on this epsilon. If epsilon is small, this is small. Okay, so this has no dependence on t and x, which means that even if we vary t and x arbitrarily with epsilon, as epsilon goes to 0, we let t and x fly away to infinity in an arbitrary manner. Q epsilon of t epsilon x epsilon is still going to 0 in probability. So Q epsilon at t epsilon x epsilon is just the heights at x and its nearest neighbors minus the average height, this vector at time t and x. Okay, and so this vector is going to 0 in probability as epsilon goes to 0, even if you let t and x vary arbitrarily as epsilon goes to 0. Okay. So since this is this vector, this shows that we can apply this Taylor expansion and get what we want. And then some more work is needed to establish the remainder term is negligible compared to the other terms and so on. But this is the heart of the argument. So to show that this approximation holds. Okay. So this is roughly the sketch of the main part of the proof, where I show that you have this. And and then there are other things that you can think of after this. So I'll omit that. Okay, so I think that's all I have to say. Thank you.
Thank you very much, Sourav. Very beautiful talk. Let's think. Is there any question?
So I have questions, Sourav. Thank you very much for this talk. Well, there's something which I did not understand. So it's could you comment on this? The fact that there is no way that you can scale to get the KPZ equation that you mentioned. I didn't get that. And then also you said that, well, if your function phi was not C2, you might get something else. Could you comment on that also?
Yeah, so the second question, if phi is not C2, so in my paper with Suganidis, so I have this first paper where I look at this whole setup without the noise. So I was trying to understand what happens if you don't put any noise. And if you don't put any noise, you can prove an actual scaling limit of this whole process to a deterministic system, which is a deterministic KPZ equation. So you have the KPZ equation without the noise. It converges to that. And then in my paper with Suganidis, we looked at phi, which is not C2, various other kinds of phi. Let's say phi is the maximum of the coordinates or the minimum of the coordinates or the median of the coordinates, okay, of the heights at neighboring locations. So we look at all kinds of things. And you get all kinds of strange equations coming up. You don't see the KPZ. So you see, other actual new equations, and that's what Suganidis tells me, that you get new equations that people don't know, coming up from that. So that's very interesting. So I don't know what will happen in the continuous if you add the noise. So I don't know what's going to happen if you add the noise. But if you don't add noise, you do get these other strange equations if you don't have the C2 assumption. So that's the first thing. And the other thing is, about this these coefficients. So let me go back to that. Yeah. So you have these coefficients nu, lambda, and d here in the KPZ, and suppose so in the paper of Albert-Scanin and Quastel, they get this KPZ limit and they have this constant coefficients in front. So it looks exactly the KPZ equation as it is presented. Okay. And then the physics keep telling us, and there are various other indications that in 2 and higher dimensions, you cannot keep the coefficients constant. So you cannot define KPZ as it is written down in the KPZ paper. You need, so suppose you want to define KPZ, but let's say, instead of white noise, you take some colored noise, you take a little bit of modification. And as you send the modification to 0, you need to vary the coefficients in front of the terms with that. You need to send something to 0 or something to infinity, to get some meaningful limit. And so this is sort of coming up here. So that was the point. So suppose even in this local KPZ behavior, suppose you want the coefficients are all of order 1. They're bounded above and below by constants as epsilon goes to 0. So we have these formulas for them, and we want them to go to 0. So then I deduce that we will end up with this condition, that epsilon squared beta to the d minus 2 has to be of order 1. And beta is going to 0 as epsilon goes to 0. And so there is no way you can ensure this if d is 2 or higher. Okay. So there is no way to do this. You can do this only if d is 1. And even if d is 1, there is only one way to do this. That is, beta should be epsilon squared. And then these formulas will tell you that alpha should be epsilon to the 4th and gamma should be 1. And if you consider the polymer model, this just gives you the intermediate disorder regime. So the regime that Albert-Scanin and Quastel did is somehow the only regime where you can get these constant coefficients. So in their paper, they mention, so I'm not very clear on this, but in their paper, they mention that there may be some other ways of getting scaling limits of these directed polymers, even in 1 dimension. So there may be other scaling limits. But if there are other scaling limits, they cannot have a constant coefficient. So the coefficients need to vary with epsilon as you send epsilon to 0.
I see. And then one minor question. So you define the Laplacian taking the average instead of taking the value of a point. Why?
Yeah. Okay. So this is it's in the gradient squared. So the Laplacian is fine. So let me go back to that. Yeah. So the Laplacian is the average minus the value at the point, and that's the usual definition of the Laplacian. But the gradient squared is you take the value at a neighbor minus the average value divided by the distance squared. And if epsilon is converging to a smooth function, it doesn't matter. Whether you put the average value or the value at the point, they all converge to the gradient squared. Okay, but it does make a difference if this is not converging to a smooth function. And this is sort of the situation like the Ito versus the Stratinovich integral. So if you put the value at a point instead of the average value, it makes a difference. The local behavior, instead of being KPZ, you get an additional Laplacian squared term. Okay, so you get a slightly different, something else coming up. So you don't exactly get the KPZ. And this kind of subtle difference, random processes have these things that how you define, the discrete approximation to a smooth thing, may give different results for different discrete approximations.
Well, thank you. Thank you very much.
Thank you. Okay.
Is there any other question or comment?
So maybe I just have a follow-up question. Nice talk, Sourav. So for the 2D equation, so there's no way to make meaning of that. I think you had mentioned something at the beginning of the talk about. So I mean, so you can't have all three. The Laplacian term, the square term.
So you cannot have all three things constant. So that's at least in local behavior, you cannot have that. That's what this shows. Maybe in the global behavior, you can have something, but I doubt that, because the things that you see in the physics literature, they all have coefficients going to zero in some way, as and in the things that have been constructed, these distribution valued solutions that have been constructed also have this property that you have to send some coefficients to zero, or at least one coefficient to zero, to get some kind of meaningful limit.
So if you redefine that gradient without using the average, would something different occur in terms of these scalings?
Not in terms of the scaling. So you get a different equation, as I said. You get an additional Laplacian squared term. So you have the Laplacian plus gradient squared plus Laplacian squared plus some noise. So that's what you get. And I didn't quite investigate what happens with the coefficients in that, but that's maybe worth investigating.
Okay, thank you very much. Nice talk.
Thank you.
Any other question?
I have a brief question. So several moments in your idea of the proof, I was reminded of Lindenberg's CLT proof. And I wanted to ask if there is something that can be done. For example, if you know the scalings, if you assume the scalings are such and such for a given noise, and you replace that noise with another noise that has the same moments up to a certain point, then you get some universality.
So here you already have the universality in some sense, because I'm just assuming the noise variables are mean zero, and so the main assumption is that it's bounded and have absolutely continuous density. So I'm not assuming a specific distribution of the noise. And the KPZ limit that you get in the coefficients that you get don't really depend very much on the noise distribution, except for that is mean zero, and it depends on the variance of the noise. So you already have the universality in that sense in this setting.
So changing the noise does not change the scaling.
No, if you keep the variance the same. The only thing that can be improved here in this particular question is that if the noise can be made unbounded, because I do work with bounded noise.
I see.
Okay.
Interesting. Very nice talk. Thank you.
Thank you.
Any other question? I have just a comment. Is the process that you are taking of the local average plus centered random variable, it was studied by Hammersley, I think in the 80s or 70s. He called them a harness process. I don't know.
Harness process. Yeah, I've heard that term. I see. Okay.
Nice. And then this has some kind of duality similar, but much simpler than the one that you described with the random walks going back in time.
I see. I should look that up more carefully. I see. Thank you.
Okay, welcome.
Okay.
Is there another question? No. Okay, so let's thank Sourav again. Thank you, Sourav. Very nice talk.
Thank you. Bye.
Bye-bye.
Bye-bye.